Counter-current multiplier system. We will explain the counter-current multiplier system of the loop of Henle, which creates high osmotic pressure in the renal medulla. In most parts of the body, the interstitial fluid osmolality is approximately 300 milliosmoles. This is approximately the same as the osmotic pressure of plasma in blood vessels. Osmolality is determined by the concentration of sodium, glucose, and urea nitrogen. On the other hand, the osmolality of urine changes depending on various bodily conditions. For example, when the osmotic pressure in the body decreases due to excessive water intake, the kidneys produce hypoosmolar urine of at least 50 milliosmoles, which excretes water while retaining electrolytes. This is only 1/6 of the normal osmotic pressure of extracellular fluid. Conversely, when there is a lack of water in the body, the kidneys increase water reabsorption and decrease urine output, while continually excreting eluates, producing concentrated urine. When there is a lack of water in the body and the osmotic pressure of the extracellular fluid increases, 1200 to 1400 milliosmoles of urine can be excreted. The ability of the kidneys to produce urine that is more dilute or concentrated than the osmolality of plasma is essential for the survival of land mammals, including humans. This regulation of urine osmolarity is achieved by utilizing the high osmolarity of the interstitium in the kidney medulla and allowing water to be reabsorbed in the collecting ducts. So how is this high osmotic pressure in the kidney medulla achieved? This illustrates the proximal tubule, descending loop of Henle, ascending loop of Henle, and distal tubule. First, assume that all of these sites are filled with a solution with a concentration of 300 milliosmoles, which is the same as the osmotic pressure of plasma. In addition to this assumption, we would like to confirm 3 premises of physiology of renal tubule system. Premise number 1. The ascending limb of Henle's loop has an active transport pump that moves sodium and chloride within the lumen of the ascending loop of Henle into the interstitium. As a result, concentration of ions in the tubular lumen decreases in the ascending loop of Henle. Conversely, the concentration of ion in interstitial fluid increases. This active transport pump, which moves sodium and chloride, can create a concentration gradient of 200 milliosmoles between the renal tubular lumen and the interstitium. Premise number 2. The descending loop of Henle has low permeability for ions and urea, but high permeability for water. Therefore, water molecules easily move due to the difference in osmotic pressure, and the osmotic pressure inside and outside the membrane reaches equilibrium. On the other hand, the ascending limb of Henle's loop is permeable only to ions and not to water. Premise number 3. Raw urine with an osmotic pressure of 300 milliosmoles filtered by the glomerulus constantly flows from the proximal tubule to the distal tubule. When raw urine with an osmolality of 300 milliosmoles reaches the ascending loop of Henle, active transport pumps transport sodium and chloride to the renal medulla. The pump is capable of creating an osmotic pressure difference of 200 mmosmolar across the membrane, thus creating an osmotic pressure difference of 200 mmosmolar between the renal medulla and the ascending loop of Henle. That is, the osmotic pressure of the interstitial fluid in the renal medulla is 500 milliosmol.
When the osmolality of the interstitial fluid in the medulla increases to 500 milliosmoles, an osmotic pressure difference occurs between the interstitial fluid in the medulla and the raw urine in the descending limb of the loop of Henle. However, the descending limb of Henle's loop has a high water permeability, so water molecules move quickly and the difference in osmotic pressure between the inside and outside disappears. As a result, the raw urine of the descending limb of Henle's loop becomes concentrated and reaches equilibrium with the osmolarity of the medullary interstitial fluid. The osmotic pressure of raw urine flowing through the descending limb of the loop of Henle increases to 500 milliosmoles, the same as that of the interstitial fluid of the medulla.
The raw urine concentrated to 500 milliosmol in the descending limb of the loop of Henle is pushed to the ascending limb of the loop of Henle by the raw urine flowing in from the proximal tubule. There, sodium chloride ions are transported to the medulla by active transport pumps until an osmotic pressure difference of 200 milliosmoles is reached. As a result, the osmotic pressure of the interstitial fluid in the medulla increases to 700 milliosmoles. Due to the high permeability of descending limb of Henle loop, the osmolality of raw urine quickly reach equilibrium. By repeating the above process, the renal medulla increases to a maximum of 1200 milliosmol. In addition, the difference in concentration due to the pumping of sodium and chloride from the ascending limb of the loop of Henle, and constant inflow of raw urine having the relatively low osmolality of 300 milliosmol into descending limb of Henle loop result in osmotic pressure gradient within the medulla. Above, we talked about the counter-current multiplier system, which creates high osmotic pressure in the renal medulla. Thank you for your listening. Goodbye.